Thank you for having me here. I'm really excited to present my research through this opportunity. It's really great to connect with fellow Korean women scientists, and I did not know this avenue existed, so thank you so much for inviting me here. Today I'm going to talk about human-building interaction for intelligent building operation. This is one of my research areas, and I'm really excited to share some of my recent research findings. First, we should probably talk about why this is important. It's because buildings are where we spend 90% of our time, which has huge implications on our comfort, health, and productivity. Certainly last 3 years were an important reminder of this reality as we spent an enormous amount of our time in our respective home. So providing satisfactory human occupancy is obviously a primary function of most buildings. And for that, buildings use a lot of energy. 36% of the global energy use, to be specific, and also buildings are responsible for almost 40% of carbon dioxide emission. It's tempting to blame other sectors like transportation and industry for this carbon emission, but buildings aren't that innocent in this whole conversation. So, what do people think of their own building, considering how much effort and money goes into creating and maintaining these buildings? And I think it's a fair question to ask. According to a large survey data that we did at UC Berkeley, buildings are generally performing well, but the thermal conditions are not. And the only thing that's lower than this thermal condition is speech privacy in open plan offices, which I think all of us can relate to because we've been to a place where we had to share the open space with a lot of people. This is quite unfortunate because 30 to 40% of the building energy use goes towards space heating and cooling. I'm in Canada, which is a colder climate. We spend more than that, almost over 60% because of our long heating season. 들리시나요? 네.
네, 잘 들립니다.
네. But here's the reality about building energy. Yes, it's important. Reducing it is certainly an important goal of our society, but it's still a small part of the building economics. In fact, for any companies that have an office space, they know that the cost of salaries is far more than the cost of energy. We're here talking about 100 times more. So things that impact people's comfort, health, and productivity can have a big influence on our day-to-day building operation decisions, even if it could unintentionally drive up our building energy use. The irony is that we don't usually design buildings with end users in mind. This is quite evident in many building systems, including HVAC, that are based on large thermal zones, which could span several rooms, hallways, and open space. And its primary goal is to deliver constant, uniform conditions across the entire space. And most of the time, we do not consider individuals' preferences or requirements. The control of these systems are not very user-friendly because they're often not readily accessible. A good example is a covered thermostat that you probably found in many buildings where the facility managers do not want you to control. They often lock it and you need a key to access. Even if it's accessible, often we need to share this thermostat with many people in the same space. And that can be quite challenging if you and the person across from your desk cannot agree on the temperature. Some people get really frustrated and they take the matter into their own hand by bringing a personal fan, sometimes a space heater, which is horrible for the energy consumption. Sometimes you will see a person blocking the air vent so that they don't experience the cold draft from the HVAC system. And all of this can result in a negative impact on both energy and overall comfort in the space. So, what is important to occupants and what do they care about? Well, it's often what surrounds their immediate environment. We care about our thermal, visual, and acoustic environment quality, as well as indoor air quality and often smell. And all these can have an impact on our comfort and productivity. Of course, there is growing interest in health and wellness. These are very important issues these days. So there is a lot that we need to consider when we're designing a building. Unfortunately, that's not quite aligned with how we design our buildings. We want to bring more positives into our built environment, but the current practice focuses on how to minimize the negatives. In fact, many design values in standards and codes are based on universal models in order to achieve the lowest dissatisfaction among building occupants, which I think is a pretty sad place to start the whole conversation of building design. We also do not consider diversity in our needs, preferences, and health conditions, even though these things can drive up the energy consumption once the building is done with the design and construction phase and goes into the operation. This kind of thinking continues even in building research, where occupants are often treated as a source of noise, heat, moisture, and CO2, as far as energy models are concerned. And we like to schedule them to behave in certain ways. For example, when people are supposed to enter and exit the building, and all of these inputs inform our building system sizing and the choice of the type of systems that we want to put in the building, as well as the control logic. So obviously, there's a lot of assumptions go into this energy modeling for buildings. But the reality is that humans, we do not act like a passive recipients of what's already created for us. We often interact with our buildings, and that could be simple opening and closing the windows, changing thermostat set points, and turning on and off the lights. So given that we are already interacting with the buildings, it is important to recognize this two-way interactions in the building design and operation stage. And we should also think about how we can guide this interaction so that it will maximize the building energy efficiency and system operation as well. So human building interaction as a research field is born out of this need to allow the built environments to learn, adapt, and evolve with its users. As you can tell, it's highly interdisciplinary because it requires an understanding of not only engineering and architecture, but also human factors, computer science, and perspectives from social and health science as well. What we've been noticing in the past decade or so is the tech companies starting to really pay attention to this problem. and rethink building controls and their interaction with humans. One of the first initiatives from these tech companies was to connect building systems and devices to the internet. So we see thermostats like Google Nest and Ecobee being online. Another innovation these companies have brought to our world is the diversity in control interfaces, such as smartphones, tablets, and even our own voice that can act as a way to interact with our buildings. And lastly, data and learning. These companies are collecting data to have a better understanding of what's happening in the building space and use that to learn our preferences and schedules and habits. And ultimately, the goal is to automate certain control sequences in order to improve the building service quality and our satisfaction. So there is a lot of research activities in this field because buildings are inherently a data-rich environment to begin with. And the Internet of Things, sensors, and devices really simplify this data gathering process at a really reasonable cost. So, so that's the field that I am in, and we're seeing more interest from other disciplines like computer science and electrical engineering, even healthcare, public health in this research field. And COVID definitely expanded the horizon of its applications because the role of buildings in health and productivity is really being recognized these days. So that was an overview of where we are in terms of human-building interaction and some of the recent innovations. Now I'm going to switch the gear and to give you some examples of my own work in this area, specifically focusing on personalizing occupant analytics and personalizing heating and cooling in our buildings. Okay, so in terms of thermal comfort provision in the building industry, we go by the international standards. The one that I want to show is the ASHRAE 55, which is an American thermal comfort standards, which is also adopted widely around the world as well. So this standard uses universal comfort models that uses the average comfort of a lot of people. And the most well-known model is PMV, stands for Predicted Mean Vote, which expresses how cold and hot we feel in terms of the heat transfer between our body and the surrounding environment. The second model that the standards include is called adaptive models, which account for our ability to adapt to variable conditions in naturally conditioned buildings, meaning if we don't have AC, then we expect less from the building. Both of these models have been successfully adopted into international standards like ASHRAE 55. This is what we go by when we size the HVAC system and the type of HVAC system. The problem is that these models have many challenges when we try to apply it in day-to-day building operation. The first challenge is that it has quite poor predictive performance because they are aggregate models designed to predict the average response of a large population. So when we apply these models to a small group of people or individuals, which is often the case for many buildings that we use that are zone-based, these models fail to predict accurately. In fact, a recent study showed that these models only achieve 30% prediction accuracy, which is even worse than a coin flip at this point. Second problem is that a lot of variables that are included in these models are difficult or expensive to measure, such as air velocity and occupants' clothing and metabolic rate. So what happens in the design stage is that we assume these values and fix it, which lead to, again, the accuracy problem when we apply it in day-to-day building operation. Lastly, these models are fixed in their properties and variable set, meaning they don't modify or adapt to specific comfort situations. Even if we find a new variable that better predict our comfort, the models are not able to take those new variables. So a few years ago, as part of my doctoral dissertation, I developed a new approach to thermal comfort modeling, which is called personal comfort models that can predict individuals' thermal comfort responses. Here, the focus is on relevant information that we can collect from our everyday environment and automate that data collection through IoT sensors and devices. And lastly, use machine learning to learn individuals' preferences and improve the prediction accuracy of the model. To demonstrate how this new framework works, I developed a set of personal comfort models for 40 office workers who participated in my field study. Through this field study, I collected a lot of data where I was able to use individuals' heating and cooling behavior, local environmental measurements, and survey responses in order to develop these models. And I also used different types of machine learning algorithms and then predicted their own thermal preference responses. And the outcome was a very predicted, but surprisingly performing far superior than the universal models. So here in this slide, you see the 6 top bars representing personal comfort models using different machine learning algorithms. And the bottom 2 represent the conventional models, PMV and adaptive, that are being used in the international standards. Each bar shows the range of predictive accuracy between 0 and 1, where 1 is perfect predictability. And as you can see, personal comfort models outperformed the conventional comfort models almost by 40% in greater prediction accuracy. These models can be part of occupant-centric environmental control, where we use various IoT sensors and devices to continuously collect data from our everyday environment and learn individuals' comfort preferences. And ultimately, the goal is to integrate these models in the HVAC heating and cooling control. And there were a lot of follow-up studies based on my research. And the follow-up studies have shown that fully integrated models can reduce HVAC energy use by 10 to 50%. Here are some current research that I'm focusing on. I'm expanding my framework to include other indoor environmental quality as well, like visual and acoustic and other type of IAQ factors as well. And also using physiological sensing to to understand the relationship between IAQ and occupants' health and wellness as well. Extreme weather conditions are being a big concern around the world. In Canada, we've had some pretty bad weather events that killed a lot of people on the West Coast So understanding how thermal safety is among different population segments during heat wave events is a big topic, and this is one area that I am focusing on as well. And also not just the healthy individuals, but what about seniors, children, and patients? How do they respond to the thermal environment? And that's another area of research that I'm focusing on. That leads to the discussion of heating and cooling systems. If I think we've all been there, where we share space with another person in a centralized system where I feel a little warm and the person next to me feels a little cold, and we have one thermostat. So what do? Online thermostats can solve this problem to a certain degree. At least, it will allow us to control the thermostat, but it doesn't solve the inherent problem of having this conflict in thermal preference. So the idea that came out of this situation was, can we personalize heating and cooling? And that was another topic that I focus in my research. So personal comfort systems, PCS, is decentralized thermal control, where individuals own their personal device to heat and cool our immediate surrounding. Sorry. Some devices are readily available, like desk fans, portable ACs. Some devices are still research prototypes, like heated and cooled chair, thermally activated clothing. PCS can also include ceiling fans that are under the control of individuals or small group. The benefits include high comfort satisfaction over a wide range of temperature and energy savings by expanding thermostat set points by 2 to 3 degrees. And every degree that we raise can save about 10% of total HVAC energy use. The PCS device that I helped to design and develop at UC Berkeley was heated and cooled chair. This was a conventional mesh type office chair where we installed fans and heating strips, as well as recharge of battery, and also we designed the hardware and software in order to collect data from this chair. The chair itself is really energy efficient. Even at its maximum setting, it only draws 14 watt, which is significantly less than how much energy a conventional HVAC system uses for each person, which is about 500 to 1,000 watt. So this is a very low energy heating and cooling system. Because we turned that PCS into an IoT device, we were able to capture the data from each chair that we deployed in our field study. And it was able to tell us some interesting stories about how individuals' heating and cooling preferences actually work in their own office. So this is one example, a snapshot of how a person used the chair during the course of one day. The red line shows the heating system, and the blue line shows the cooling system that they were using in this chair. This person came into the office around 8 a.m. and immediately used the fan to cool down from perhaps, the person's morning commute, where the metabolic rate was a little bit heightened. But about 15 minutes later, this person actually switched from cooling to heating and then keep the heating for the rest of the morning until around noontime. She uses fan again. And that kind of coincides with the temperature in the background rising. So as you can see, a person's thermal preference change even during one day, depending on the time of day, depending on the person's metabolic rate, depending on the temperature in the background. And this chair was deployed throughout the building, and 40 people got to use this chair for 3 months. And therefore, we were able to collect a ton of data, continuous PCS, chair heating and cooling. We also collected survey responses and also HVAC settings in the background. That gave us a very big, unique data set to analyze. Here is a chart that shows how all my field study participants used the chair during the course of 3 months. Each bar shows the percent heating in orange and cooling in green. Gray is none when they didn't use anything, but still was sitting in the chair. As you can see, some people use the heating predominantly, as shown in the orange bars, while other people used cooling predominantly, as shown in green bars. And this usage pattern varies a lot between individuals, even though they were more or less exposed to the same kind of indoor conditions where the temperature was quite mild, anywhere between 22 to 24 degrees Celsius. So even in a mild condition where everyone is pretty much subjected to the same environment, we can see that there is a lot of individual differences in what we want in terms of heating and cooling. Another interesting finding is that most people use the chair, fan, or heater during the first 5 minutes of sitting in the chair. And that's not quite surprising because often we walk to our office and our metabolic rate is heightened. We just, need to cool down for 5 minutes to 10 minutes, then we're okay, and we can turn off the cooling device. So that's sort of what we saw, and it also works with heating in wintertime, where we come from a really cold outdoor condition, and then we walk into our office. We just want to be warmed up just for 10 minutes, and we're okay. We stabilize, and we don't need that cooling and heating anymore. Imagine doing this kind of heating and cooling using the central system. That will be really energy intensive, and it's not going to agree with a lot of people in the space. So we were able to see that individuals really need heating and cooling sometimes just briefly, and personal comfort system can really work beautifully in that kind of setting. PCS users were really happy with the device. We were able to see 96% thermal acceptability, where they were happy with the environment, and they were also very satisfied with the device's heating and cooling functionality. Although this number, it seems like, okay, it's obvious, but this number is really, really hard to achieve with central HVAC systems, because we have a lot of survey data for the past 40 years. At most, we will be getting only 40% of the buildings that ever participated in this large survey data met 80% satisfaction. And the goal for the standards is to achieve 80% satisfaction among occupants, but that is already a very difficult bar. But with PCS, pretty much all lab studies and field studies have shown high 90 satisfaction. So PCS is being recognized in both academia and industry alike. And now PCS is being adopted into the international standard. Recently, I was working in the working group to come up with the draft language for the PCS inclusion in the standards. And now we have the new language for PCS to recognize buildings that provide greater occupant control over their indoor environment. And we're hoping that green building certifications and WELL standards will eventually adopt this language in order to reward buildings with PCS to provide greater occupant satisfaction. I'm part of this new project by International Energy Agency, project called ANEX 87, in order to work on further questions about PCS. For example, who's going to certify this device for buildings, and who's going to accept the responsibilities once it is part of the building operation, and who's going to maintain, and who pays for it. So some of these questions are being investigated. And for me, my role is a subtask leader where I focus on the technology piece of PCS. Yep, so that's the last slide, and that concludes my presentation. I welcome any questions you may have, and we can switch back to Korean.